Hello, everyone. So I'd like to welcome you here to the first session of the summit, where we'll have talks on the topic of different perspectives onto the IoT ecosystem, focusing in that order on power, on security, and on using it. Our first talk will be by Laura Marie Feeney from Uppsala University, who will be talking to us about storing energy for embedded device. Welcome, and the floor is yours.
Okay, so first confession, I am not a RIOT programmer. I've done work in embedded systems, low power protocols for quite a long time. But what I finally got, please stay closer to the microphone. Okay, so I've been doing embedded systems, low power protocols, and everybody goes along and they somewhere in the future work section of the paper, they go, yeah, but batteries aren't really linear and we should probably figure it out sometime. Okay, some idiot tried to figure it out. If she'd known what she was getting into, she probably wouldn't have done it. The point is that we need to do better than Coulomb counting. We need to do better than just saying, how much energy are we consuming? We need to understand how the battery is involved. Energy storage device is a complex electrochemical system. And so the first thing I'm going to try to do is be a little bit pedagogic and try to motivate some of the macro scale battery behaviors that we want to take into account when we're building IoT systems that we want to last for a long time. I'm going to talk about batteries, supercapacitors, what are called hybrid lithium-ion capacitors, ordinary capacitors. And one of the things I'm going to introduce is something called the Ragone plot, which is something that encapsulates sort of a fundamental trade-off between power and energy, between being able to draw high currents and being able to store a lot of energy. Then I'm going to come back and talk a little bit about why IoT applications are special from a battery perspective, why we can't just go to the battery people. There's a ton of them. They do all sorts of really good work. They work with electric vehicle people. They have more money than God. Why can't we just go to them and take their stuff? And I'm going to argue that IoT applications are different for a couple of reasons. One of which is that they're characterized by intense pulse loads. I think everybody here's worked on various protocols. You know that you try to put the device to sleep as much as you possibly can, spends a long time in a sleep state, and then it wakes up and draws a lot of current really quickly. A lot being relative to the size of the battery, but it's an unusual pattern of load to put on the electrical chemical system. The other important thing is that these are very constrained devices. We all know that, but that's going to have some implications for how the device interacts with its battery that we don't see in a mobile phone, that we don't see in a laptop, that we don't see in an electric vehicle. And then finally, I'm going to talk a little bit about the UU-CoRe Battery Testbed, which is how we got some of our results. And I'm going to run out of time, but if I don't run out of time, I'll talk a little bit about our ongoing research in organic batteries. So as a community, we are very good at modeling energy consumption in IoT. We simulate devices very well. We do statistical modeling of the node activity. What's the environmental phenomenon? How much sensing do we need to do? How much communication do we need to do? So it's kind of at all levels of the system. We model the radio, we model the application. And then basically what we do is we take all of that information about activity and we just assign currents. We just look them up in a data sheet. Or if we're a little bit cooler, we actually measure it. We've got a lot of specialized hardware out there now, both commercial tools, things like NRF power profiler, things like OTI boxes, research stuff. I think Carlo Buono's group in Graz does a lot with that sort of instrumented work. And we collect traces. So these are some traces that I did for another project, measuring narrowband IoT radios. And this is the sort of thing I think most of us do. You simply measure the current consumption. This was sending a packet under good channel conditions and under very bad channel conditions. Almost a factor of 10x difference. And that's why it's sort of very hard to estimate your power consumption just from how much work you did externally. Sending one packet can vary enormously in what it's going to cost you. But basically, our battery model, we call this kind of the state of charge. How much current did we consume over time? We integrate current over time. And basically, we say that when we run out of charge, our device fails. So charging adds charge to the bucket. Doing things takes charge out of our bucket. Effectively, Coulomb counting just means that you're treating your battery as an arithmetic store of charge. It's just bookkeeping. And listen, as a community, we've sort of said, that's good enough. Batteries are hard, but we'll call that good enough. And I think we could do better. Because we use that assumption that we can just count charge in a lot of places. When we're doing design or performance evaluation, effectively what we try to do is we try to minimize the number of coulombs, the amount of charge, for whatever figure of merit we like. Application bits user application bits within a certain time limit, whatever figure we're trying to maximize. And that's also how we look at the lifetime. We say, okay, how many operations, how much charge do they consume on average? How often do they happen? That's our lifetime. And then we say, okay, that's how big a battery we need, or that's how long our system will last. The other thing we try to do is we try to balance our energy harvesting and our node activity. How big a solar panel do we need to collect charge versus how much are we going to do? Something else that we want to be able to do is we'd like to be able to predict or manage the nodes in real time. Are some of my devices running out of power? Do I need to change how my application behaves? And all of this work that we do as a community depends on that Coulomb counting model. And I think that's a little bit of a problem because batteries are pretty complicated. I don't want to spend a huge amount of time on pedagogy. I'm happy to talk to people. I've done some battery tutorials, so if people want to go through a longer tutorial, I'm happy to do that. I think I'll be here for a while tomorrow. But this is basically what a rechargeable lithium-ion battery looks like. We have the cathode, we have the anode. And the way the earlier researchers talked about it is they talked about it as a rocking chair. We're going to move the lithium back and forth, rock it back and forth between the electrodes. And moving those positive ions back and forth between the electrodes causes a corresponding movement in the electrons through the load. So if you want to look at it one way, the electrical engineers care about the electrons, the chemists care about the lithium ions. And what happens is that as we move the lithium ions through the electrolyte from one electrode to the other, there's a process that happens, and it's the word for it is intercalation. And what that means is that we're binding into a layered structure. This is graphite over on your left, and a spinel, a lithium metal oxide in the cathode over on the right. And most of what you want to understand about batteries comes from the idea that you have to move the lithium into and out of those structures carefully, gently. Otherwise, you either damage the battery or you catch fire. And so I don't want to go into a lot of details. I'm happy to talk to people who are interested. That's sort of the basic idea behind what the battery is doing. Or if we just want to make it a little simpler, when we're discharging, we've got graphite, the carbon mesh, and that's full of lithium, and we have an oxidized lithium metal oxide in the cathode. As we discharge, what we do is we break down that lithium. We break it down into a lithium ion and an electron. The lithium ion migrates through the electrolyte. The electron migrates through the load. That's current. And to the positive electrode, and we reduce that metal. Usually those metals are what are called transition metals because they're very good at transitioning from one oxidation state to another. They're very flexible about how they bind. And so what happens is that we break down, we move that, and that flow of charge is what we call current. Power, product current and voltage. And the voltage difference between the two electrodes is a property of the material in the electrodes less any accumulated resistance that is built up in the system. I stuck the periodic table in there because I almost always get a question where I want one. When we charge, we do the opposite. We've got positive electrode is full of lithium metal oxide, and we have graphite in the anode. As we charge, we apply a voltage. It breaks down that lithium metal oxide. We see we move the electron, we push the electron through the load. That's what our charger is doing effectively. And the lithium has to follow. And again, then we intercalate that lithium and electron, lithium ion in the electron back into the electrode. And that process is actually how you blow things up charging. If you push that lithium into the graphite too hard, too fast, you push too much in, it can't bind in properly. The lithium starts binding to itself. And if enough of that happens, essentially what you get is you get lithium metal teeth called dendrites building up in the battery, and they short internally in the battery. Boom. So hopefully I've convinced you that there's some interesting things here going on in the battery. And there's this idea, if you kind of take one battery thing from the lecture that helps you remember, it's this idea that we need to move the lithium gently between these electrodes because we have to bind it into these complex structures. That if you want a take-home message about how batteries work, that's a good one. And I like using that because I think it gives you a good anchor for thinking about how batteries work. And the way a battery behaves depends on the timing and intensity of the load that you apply to it. You can't just treat it as a bucket of milliamp hours. And some of the things to think, so we usually talk about the C rate current rather than an absolute current. And that's a current relative to the size of the battery. So we don't talk about a 50 milliamp current, because if you have a 5,000 milliamp hour battery, that's a tiny current. If you have a 20 milliamp hour battery, that's a huge current. So we usually talk about the C rate current as a current relative to the nominal capacity of the battery. And then we think about a couple of important effects. Rate capacity, the faster you draw current, the faster you try to move charge, the less of the available capacity you can get. You start building up resistance in the battery, you start blocking those diffusion processes, and you can't get the charge you want. And charge recovery. Intermittent pulse loads increase the available capacity. And just to look at what's happening, if we think about a pulse load, we have some current, we come from zero, we turn on our current, we have a pulse, we get an immediate voltage drop. As we continue to draw current, we don't get a flat voltage response. We get a sort of an exponential. You can usually sort of approximate it as an exponential or some function of exponentials. When the current goes away, you get a partial recovery and then a long, slow recovery. And it's electrochemical relaxation, and that's the battery starting to come back to equilibrium as the active species, as the lithium and all of the other chemicals that are supporting these reactions continue. And so what happens is that if you have a longer duration load, you have that diffusion process going on longer. You get a bigger voltage drop. You have a smaller current, you'll have smaller drops. The other thing that then becomes important is the state of charge in the battery. As the battery begins to run out of charge, that goes from being fully charged to almost fully discharged, it's harder and harder to move that lithium around. It's hard, there's less of it there, it's harder to get out. It's harder to get out of the anode, it's harder to push into the cathode. And so the same load that creates one response early creates a much bigger response, a much bigger voltage drop later. And we can sort of divide this into kind of phases. We have the initial voltage drop due to the internal resistance, we have this diffusion process, and we have this recovery process. If you're curious about how that looks in real life, these are measurements of a lithium-ion hybrid capacitor. I'll talk a little bit about those a little bit later. And sort of a narrowband IoT-like packet. I've got a set of five of these hybrid capacitors. We apply that load repeatedly, and we can see the response voltage response. It's basically the same sorts of shapes I was talking about before at the fourth packet or fourth logical packet. By the 4,000th logical packet, we can see that the voltage has dropped, but also that the individual responses, the kind of the shape of the response is changed. We're also seeing a bigger spread between the behavior of the different cells. They're not identical. Now we get up to about 8,000 packets. Again, we just keep doing the same thing. 5 minutes. We keep doing the same thing, and we get bigger and bigger responses. So one of the big trade-offs here, if we think about this, is there's a fundamental trade-off between energy and power density. If we pack more and more lithium into the system, if we are tighter and tighter, having fewer and fewer molecules that aren't essential, it's harder and harder to move that lithium quickly. And so that's what a capacitor does. A capacitor, we just put the charge on a plate. Supercap, what we're doing is we're building a very, very small plate. I've been nice to talk about it, but I really don't have time. A supercapacitor basically builds its layers out of polarized molecules in an electrolyte. So it behaves a little bit like a capacitor, a little bit like a battery. And so this is called a Ragone plot. It's a log-log plot between specific power and specific energy. Capacitors, we can get the energy out really quickly. We can draw relative to its weight, very, very high currents. Batteries, we can draw very low current. We can put more power in. And that's a fundamental trade-off. And that creates opportunities for IoT batteries, like the lithium-ion hybrid capacitor, and like lithium titanate batteries, which are a relatively new battery chemistry. And what they do is they allow us, we don't use a carbon anode. Getting stuff into and out of carbon, really hard. We do it because it gives us a really good voltage response. So we lose voltage potential, but we can use very, very high currents. And I'll pass them around later, but we have little grain of rice size batteries that can hold 7 milliamp current. I've got some cards we can play with too. Just kind of moving a little bit to IoT applications really quickly. IoT load characteristics we said are different. We've got these pulse cycles. We're dependent on energy harvesting. And our goal is to maintain voltage in response to those pulse loads, because that's when our device is going to die, right? So what happens is that that's our goal. It's not a general response. We just want to say when we pulse, we need to stay high. And we have constrained devices. That means we don't have a battery management system. We don't have chips in our batteries like we do in a phone or our laptop. That means that our cell is really directly exposed to the device activity. It means we have really small batteries, and it means we don't have instrumentation. So when we try to maximize the lifetime, just to give you an example, we have the short load and the long load. If we have some voltage limit below which our device fails, we're good in the first case and bad in the second case. Which means that what we're really trying to do is maximize the number of pulses. And that's going to influence what type of battery, how big we need, and how we're going to do this sort of balancing. And it's also going to have a lot to do with sort of how are we going to estimate these. Just getting a current number isn't enough. And so if we think about, say, a set of loads, kind of abstract, we can think about turning that into a lot of different shapes, right? These all have the same current consumption, but very different shapes. And it turns out that things behave very, very differently. So last comment I'll try to make, how did we get some of this data? We built tools. This is the UU-CoRe Battery Testbed version 2. Built by students at TU Braunschweig. One of the supervisors was Ulf. And they're custom cards that let us apply programmable current load to a set of energy devices and record. And the difference is that they're very application oriented. battery chemists have incredibly precise tools for doing this. But if you say, can you compare 200 batteries with 15 different protocol versions? They go, huh? And that's the sort of thing that we can do. And I just lost another figure. Oh, well, this was the same problem we had before. In any case, I did not, in fact, have time to talk about my own research, which I sort of expected, but just real quickly, we're looking at organic batteries. You think about these batteries, they're very different from car batteries. We're going to put them in the built environment. They're hard to recycle. Can we replace those bad metal oxides with organically derived materials? And can we find ways to use, so PDCDA is an organic material, doesn't behave nearly as nicely. We see big drops compared to lithium titanate or straight capacitors. But hopefully we can make those work a little bit better and be more, just so I don't get in trouble, I have to get to that slide. Parts of this work have been carried out by the Swedish Strategic Innovation Program, Smarter Electronic Systems, a joint enterprise of Vinnova, Foremost, and the Energy Agency. And I got in trouble last time for not putting that on my slides. And I should also credit my colleague Christian Rohner at Uppsala University. Any questions? I also have some cards to pass around if people want to look at them. I want them back.
Question? It was quite interesting to see this challenging thing about kind of predicting the pulses and how the battery will respond to this. Where I worked, we have the same thing, but with kind of big machines like power tools. And the solution was actually a bit where my question is, what if instead of having a single battery for a single purpose, you try to make an array of very, very, very small batteries?
So there's a group in so sorry. So there's a group in Korea that tried to do that. They tried to build a composite battery that was a combination of lithium titanate, lithium ferrophosphate, and lithium cobalt. Three different battery chemistries for three different responses. Part of it is complexity. Rechargeable batteries need a lot of complex circuitry. Now you have to triple the circuitry. And again, for a lot of these IoT devices, it's the sleep current that you care about more than anything, because you spend most of your time sleeping. And a lot of these components, like DC-DC converters, sitting here, they have it's 20 nanoamps there, 100 nanoamps, 100 nanoamps here, 20 nanoamps there, and suddenly you've got a real background current. Something that people do often suggest is, can you smooth these loads by putting a capacitor in front of the battery? And the answer is sometimes you can, but it's difficult because capacitors leak. And you don't know how big a capacitor you're going to need. You saw that example I had before, where you, depending on your radio conditions, you might have a difference of 10. So it's hard to dimension that capacitor. And if you fill it up, you either don't have enough or you have a lot that's going to leak before your next transmission. So I think there are things you can do in hardware. Certainly part of the problem with these very small devices is you can't build big complex batteries, right? The car people don't have this problem. They have space for very complex software, very complex hardware, managing a huge array of batteries. So between the car driving and what's happening on the batteries, there's an enormous system in between, and we just can't do that in IoT. We don't have the cost, we don't have the space, we don't have the hardware, and again, it can be the background, that background current, quiescent current that can really hurt. Yeah.
My name is Feeney. I have a question about one of those slides. The one was with the number of cells when there were 5 graphs compared to the batteries.
Those were 5 of the same battery.
Now, my question for the site and probably the construction of batteries. So are the lithium batteries built in the same way as transformators? So what if we make the smaller? If we make the problem is when we have
This is the one you were asking about, yeah.
So the problem you know that when we put much more lithium in the battery, then it's complicated. Becomes more complicated to charge this battery and to hold this battery. So, but if these amounts of lithium will be distinguished in a smaller parts, so batteries will be much more smaller. So, like the transformators, which are built, so they are also built this way. So the metal lines are very thick, and it makes the process of the transformation of magnetic fields. Is it the same way the batteries or not?
I'm sorry, I'm not completely sure. I thought over here. So I'm not completely sure I follow. So what we have here is we have
here the 4,000 packets.
Right. We've applied 4,000 loads, and it's sort of inspired by a packet.
What?
So this is an abstract load. It's sort of inspired by a narrowband IoT packet. The behavior is sort of inspired by a narrowband IoT packet. It's not a complete replication of a packet. So I mean, a real packet has a very complex behavior, right?
So okay, maybe it's
yeah. Well, okay. Yeah, we can take it offline also. I think Christian is getting.
I think if there's one more question, we can still have that.
Sure.
Yeah, thank you. Going back to the slide with the drop in voltage for a battery that's discharged to a degree higher than usual. Like, is the steeper drop in voltage just due to the higher impedance, like due to less reactance in the battery?
It's actually quite a lot of factors. I mean, chemistry is complicated. Perhaps the most mechanical way to think about it is that you've embedded lithium into the anode, and now you've taken most of it out. So what's left in there is harder to get out, especially if you try to take it out very fast. You just can't get it out fast enough. And if you do try to get it out too fast, if you do over discharge a battery, what happens is that the electrode gets damaged. And that's why you never let your phone go to completely discharged, right? It's because you've pulled all the lithium, you're pulling that lithium out so hard that that graphite structure becomes damaged. And as that happens repeatedly, that's what battery aging is, to a large extent, is the electrodes becoming damaged over time. In the shorter term, which is what we're looking at here, essentially you're building up polarization in the electrode. So you get a big initial resistance drop as you've discharged it, and you have less lithium. It's harder to get out of the anode. It's harder to make those reactions happen in the cathode because you've already done it a lot. And again, if you try to push too hard, those metals are very reactive. If you keep pushing, they'll just keep going on and doing more reactions, some of which aren't reversible in the way that you want for recharging the battery. So you start trapping the lithium, you start trapping other compounds into the cathode. And again, that's another part of the aging process. Does that clarify?
Yeah.
A little bit, yeah.
I think we are done with questions in that case.
If somebody, I've brought some batteries. I've brought some interesting things. If people want to play with cards today or tomorrow, they are very welcome.
Well, again, thanks a lot.